Today, we're peeling back the curtain on one of the most transformative technologies of our time, large language models. So, you've probably played around with something like ChatGPT or Gemini, right? And it can feel like actual magic. You type in a question and boom, out comes this perfect, creative, sometimes mind-blowing answer. But how? How on earth does a machine pull that off? How does it get human language? And this quote from Connor Leahy really hits the nail on the head. He talks about this massive underbelly of insanity, and that's because these systems, for all their power, are just different. They don't think like you and I do. It's something else entirely, almost alien. Okay, so to really get how this works, we've got to start at the very beginning with the model's one fundamental goal. And you know what? When you boil it all down, it's actually way simpler than you might think. So here it is. At its absolute core, an LLM is just a prediction engine. A really, really powerful one. Honestly, the best way to think about it is like a supercharged autocomplete on your phone. Its entire job, its whole purpose in life, is to look at a bunch of words and guess what's the most likely next piece of a word to come. They call that piece a token. So what in the world is a token?
Right, so before a machine can do any math on our words, it has to turn them into numbers. It can't read hello, but it can understand the number 15337. That first step is called tokenization. It's basically an algorithm that chops up our text into common chunks. So a word like tokenizer might get split into token and izer. Each of those little chunks gets its own unique number, and suddenly you've got a sequence of numbers the computer can actually work with.
Okay, but hold on. Just predicting the next little piece of a word, that doesn't explain how it can write a whole essay or a poem or find a bug in your code, right? There's a huge leap from glorified autocomplete to what we're seeing. So what's the secret sauce? Well, that brings us to the key technological breakthrough that made all of this possible. You see, for a long time, these models had a terrible memory. They'd literally forget the start of a sentence by the time they got to the end. Not great for writing anything complex. But then 2017 happened. A bombshell paper drops from Google researchers with this incredible title, Attention is All You Need. And this paper introduced something called the transformer architecture. And I'm not exaggerating when I say it changed everything. So what was the big idea? It's a mechanism called attention. And it's brilliant. Instead of reading word by word and forgetting what came before, the attention mechanism lets the model look at the entire sentence or even paragraph all at once. Think about it like this. It's like a detective who can instantly see how every single clue in a crime scene relates to every other clue. So when it's trying to predict the next word, it can pay attention to the most important words from anywhere in the text, no matter how far away they are. This gives it a deep, rich sense of context that just wasn't possible before. All right, so you've got this incredible engine, the transformer. But an engine like that needs fuel, a lot of fuel. And in the world of AI, that fuel is two things, data and raw computing power. And we're talking about a scale that is just mind-boggling.
Take a look at this number, 540 billion. That's how many parameters Google's Palm model had back in 2022. So what's a parameter? The easiest way to think of it is like a little tunable knob or a connection in the model's brain. And during training, the model is constantly tweaking all 540 billion of those knobs over and over, trying to get better and better at predicting the next token. It's how it learns. And what does it cost to tune all those knobs? Well, for that one model, the estimate was around $8 million just for one training run. The sheer amount of computer hardware and electricity this stuff consumes is astronomical. And that's why, really, only a handful of giant tech companies can afford to build these massive state-of-the-art models.
So that's the computing power. What about the other part of the fuel, the data? Well, there's a rule of thumb that's emerged from the research. For every one of those parameters, you need about 20 tokens of data to train it well. So you do the math. For a 540 billion parameter model, you're talking about trillions of tokens. You're basically feeding it a massive slice of the entire internet. Books, articles, websites, you name it. So let's put it all together. You take this revolutionary transformer architecture, you fuel it with a giant chunk of the internet, and run it on a supercomputer that costs millions of dollars. What do you get? Well, you get something more. Something that goes way beyond just being a good guesser. You get a system that, for all intents and purposes, seems to understand. And this leads to one of the wildest, most fascinating things about these models. At a certain point, when they get big enough, they start developing what researchers call emergent abilities. These are skills that nobody programmed into them. They just appear out of nowhere. It's not about the model just getting better at what it was already doing. It's about it suddenly being able to do completely new things it couldn't do before. Here's a crazy example. The ability to do chain of thought reasoning, to actually show its work step by step to solve a math problem. That skill only shows up in models that have more than 60 billion parameters. Smaller models, they just can't do it. It's like a switch flips. But as you can probably guess, this kind of unbelievable power, well, it comes with a catch. It's a real double-edged sword. And why is that? Because the very same thing that makes them so brilliant is also their greatest weakness. Remember, they're built by just one principle: predict the next word based on a huge messy pile of text scraped from the internet. And that simple design creates some really fundamental problems that are just as big as their abilities.
Okay, so let's break this down. On the one hand, you have these amazing abilities, but on the other, you have some serious limitations. First off, these models have zero concept of what's true or false. They can make stuff up, what we call hallucinating, and state it with complete confidence because their only goal is to sound plausible, not to be right. Second, since they learn from us, they learn our biases too, and can even make them worse. And finally, they can be tricked. People can use clever prompts to get them to ignore their own safety rules. These aren't small issues. They're baked right into the design. Which leads us to the biggest, most mind-bending question of all. A question that even the top experts in the field are still arguing about. Are we building something that truly understands the world? Or are we just building an incredibly sophisticated parrot? Is it a new kind of alien intelligence? Or is it just the best mimic the world has ever seen? So here's what you should really take away from all this. Large language models, they're not magic. They're incredibly powerful prediction engines, built on that revolutionary transformer idea and fed a mind-boggling amount of data. And both their amazing skills and their serious flaws spring from that exact same source. So the next time you see one of these things write a beautiful poem, you'll know it's not magic. It's just predicting the next word. But that simple prediction, well, it's already changing everything.